Kia ora and welcome to video 22 in the series Insightful Integration. The question today is very much similar to yesterday's in that it's a messy integral that can't be solved using normal anti-differentiation techniques like reverse chain rule or integration by parts. In fact, we're given a trig identity here and suggested that we could make use of it. It's not so clear as to where that is useful or how it's relevant to this question, given that there's no trig in the original integral. However, it is useful. I'll leave you to think about how the hint applies by thinking about the substitution that you might need to simplify this integrand. Good luck, and we'll catch you afterwards for the video going through the solution. Okay, so this integral is an interesting one because the hint is to use the compound angle formula for tangent. Like, I look at that problem and go, where are the tans? And it's similar to an earlier video in this series where we make a substitution that doesn't actually appear in the question. So to bring in tan into this integral, I'm going to try let x equal tan theta. And if you've done enough of these problems, you'll know that making a trig substitution like this is only useful if the derivative simplifies things. And hopefully you've got a good understanding of the formula sheet and you know that sec squared theta minus tan squared theta is always equal to 1, provided that theta makes that expression defined, and theta equals pi over 2 does have some issues there. And then looking at that, 1 plus tan squared theta is in the denominator of this integral. Because if I go and differentiate differentiate x equals tan theta, I'm going to get dx equals sec squared theta d theta. So that's cool. And then I want to replace the sec squared theta d theta part. That's going to go into there. And then this x squared plus 1 thing is tan squared plus 1, which, lo and behold, equals this dude. So our integral, I'll leave the limits for now, is going to be log of tan theta plus 1. The dx becomes sec squared theta d theta, but the denominator becomes sec squared, so we just end up integrating that. Our limits now, originally x was 0. Well, x equals 0 is going to occur when theta equals 0, because tan of 0 is 0. And to get a limit of x equals 1, we're going to have to make theta pi over 4 for that one. So this is our integral that we're going to find. Now we've brought in tan into the question, but I just don't see at this point in time where does the compound angle formula from the hint actually appear. And this is where last video's reflective formula helps. If you haven't watched last video in this series, then maybe do that first. But this integral here is the same as between 0 and pi over 4 log of tan pi over 4 minus theta plus 1 d theta. So I've done the whole, this is A, this is B thing. A plus B is pi over 4, and then I've got the minus theta in. I've replaced the x, so to speak, or the original variable theta, with A plus B minus theta. Okay, and those integrals are the same, so we do the same thing as the last video where we call them both I, and then we add them. So 2I is the integral between 0 and pi over 4 of log of tan theta plus 1 plus log of tan of pi over 4 minus theta plus 1. How has that helped? Well, we've brought the compound formula in now, so we can simplify that thing. We'll do that on the side. So tan of pi over 4 minus theta. That's going to be tan of pi over 4 minus tan of theta all over 1 plus tan pi over 4 tan theta. And tan pi over 4 is 1. So that's 1 minus tan theta over 1 plus tan theta. Dump that back up into the expression. We're integrating log of tan theta plus 1 plus log of 1 minus tan theta over 1 plus tan theta all plus 1. We can put those fractions together there with the 1 minus tan theta of 1 plus tan theta. We can turn the 1 here into tan theta plus 1 over tan theta plus 1. And when we add those two dudes together, we're going to get 2 over 1 plus tan theta. So you can check that that works there. And now we've got two logs. I should really have brackets around this whole thing, by the way. Okay, we're actually integrating the whole thing. It's a minor thing really, but just for making sure that the calculus is all correct, we'll put brackets there. Now we add those two expressions using the log rule. Two logs added together is the log of the product. So we've got log of 2, because if we take this dude and we multiply by this dude, well, the denominator of 1 plus tan theta cancels out with the tan theta plus 1. So we're just integrating log of 2, and like that last video, it's just a constant. So when we integrate that, we've got log of 2 times theta between pi over 4 and 0, which equals pi over 4 ln 2. Now just be careful that there is 2 times the integral, because we added the two integrals initially, so therefore the integral, the answer to the question, is half of pi over 8 ln 2. And you can confirm that by just putting the integral into your graphics calculator or into Wolfram Alpha. It's a definite integral, so just put it in and see that the decimal you get, if your calculator doesn't give an exact form, just check that the decimal matches this exact form. Quite a neat question, but really quite a tricky one, because even though there was a hint there, it wasn't so clear how to apply that hint. We needed to bring the tan function in, and we also needed to work out where the compound angle formula came from. That reflective property probably should have been given as another hint, but I chose to leave it out because I'd already covered it. If it was in a scholarship question, you'd probably get both hints. Anyways, catch you in the next few videos where we're going to have some application type questions to finish this series off. Bye for now.